Hi, my name is Zhong, or Fangcheng. I'm currently about to finish my PhD degree at the University of Cambridge and continue as a research associate. Today I'm going to present our work reproducing reality with a high dynamic range multifocal stereo display. Let me first motivate the problem. In the past few decades, computer graphics has achieved remarkable success in photorealistic rendering. Oftentimes, it's very difficult to distinguish between photographs and computer-generated images. With such advancement in the field and emerging 3D display technologies, the next big challenge of computer graphics is to achieve perceptual realism, meaning that the displayed content should be perceptually indistinguishable from real-world 3D scenes. So how far are we from achieving this quality? Our work shows that it's actually not so far. We built a novel high dynamic range multifocal stereo display with an end-to-end imaging and rendering system. The system can reproduce virtual 3D objects with such fidelity that they can be confused with physical ones. Here, we show two photographs of the virtual objects rendered by our display next to real ones. I hope at this point it's not too easy to tell which ones of them are real, so there's more fun for you to follow the rest of the presentation. The pursuit of perceptual realism did not start from us. The Cornell box was the first to compare rendering shown on the CRT screen with the real scene. Both the real scene and the CRT screen were shown to the observers through a camera viewfinder, and the observers could not tell which image was computer-generated. This was an exciting result at the time, but it was achieved only by a monocular vision and a degradation of the real scene images, due to lens distortions and small viewer size. Another work that reported a perceptual match between a real and a displayed object was achieved by Oberg University. They also asked the observers to compare a real 3D object with a virtual one shown on a 2D display. Although the real scene was not degraded by any lens distortions, it was shown through a small aperture in a box of 2 meters long, and it only allows for monocular vision as well. Their experiment was conducted in a non-dark room because their display was not HDR and cannot achieve the desirable low black level. In contrast to previous work, we aim to reproduce a 3D object with high dynamic range and 3D depth cues, including binocular vision and correct accommodation. We also present both the real and virtual scenes in a short distance and without any degradation of the real scene. But we also have the limitations that we only consider static scenes with a fixed viewing position and moderate field of view. Now, let me introduce the choice of our display hardware in order to achieve the quality we aim for. While there are several fundamentally distinct approaches to 3D display architectures, not all of them meet the requirements for our objective. For example, holographic or light view displays have the potential to reproduce a 3D scene with accurate light distributions and 3D depth cues, but the state-of-the-art of these technologies haven't achieved the required resolution, contrast, or color accuracy for perceptual realism, despite recent excitement of leveraging machine learning to improve the fidelity of holographic displays. An alternative is to use a varifocal display. The idea is to put an adjustable lens in front of a regular stereoscopic display, modifying the focus in accordance with the depth of the gaze. This approach can achieve high resolution and contrast, but introduces undesirable lens distortions. Also, this approach requires a highly accurate synchronization between the lens optics and gaze tracking, which is highly demanding for both hardware and software. Finally, its defocus blur can only be synthesized rather than optically reproduced. Our choice is a multifocal display. The idea is actually very simple. Similar to approximating a continuous spatial domain with discrete pixels, depth can be discretized by image planes. Since human depth sensitivity is uniform in diopters, we can use a small number of image planes to approximate a reasonable range of depth. This approach doesn't introduce any lens distortions or require any optics synchronizations. Most importantly, a multifocal display only allows for a fixed viewing position, meaning that it doesn't have to reproduce an entire light field but a subspace. Because of this, it can maintain a high resolution and contrast. Our display, as the name suggests, is a hybrid of multifocal display and HDR displays. It provides a reasonably high dynamic range and resolution, as well as 3D depth cues including stereopsis and correct accommodation. Our display also has a distinguishing feature that allows for a direct comparison between virtual and real scenes, which I'll explain in a second. This is the front view of our display apparatus. The observer sees the virtual image through the stereoscope at the center. On each side of the observer, there were two HDR displays. With the optics of the beam splitters, each eye sees the virtual images of two focal planes of HDR content, one at a near depth and one further. Behind beam splitters there is a real scene box, which allows the observer to see the virtual and real scenes at the same time. We can rotate the real scene box to the side and capture a horizontal light field of it, with the data camera mounted on a slider. This photograph shows the virtual scene displayed through the beam splitters and the real scene box behind it. This is us capturing a horizontal light field of the real scene box with a camera slider. After introducing the hardware of our display apparatus, let me explain how our imaging and rendering system works to capture a real scene and reproduce it with high quality. From a high level, our pipeline is simple. We capture the light field of the real scene, encode it into a 3D scene representation, then render it to our display. We also need to perform a geometric and a colorimetric calibration on both the camera and display side to eventually achieve a perceptual match between real and virtual scenes. Let's now look into each part of the pipeline with more details. First, we capture an HDR light field of the real scene and perform a camera calibration using photogrammetry. The calibration generates the camera matrices that relate the pixel coordinates of the light field images with the world coordinates. For the 3D representation, we found LumiGraph to be the best fit for our purpose. A LumiGraph is a surface light field that can be stored as a proxy mesh with field-dependent UV maps and textures. It has the advantage that it's robust to processing HDR and high-resolution textures. It's capable of modeling non-Lambertian surfaces, and it performs rendering in real time. The disadvantage of LumiGraph is that the proxy mesh has to be very accurate to avoid rendering artifacts. Since mesh reconstruction is not the main focus of this project, we chose to work with non-geometry, such as primitive shapes or 3D printed objects, for which we have the ground truth mesh file. There were recently many exciting works on neural representations, such as NERF, which can achieve photorealistic results and is robust to complex scene geometries as well. But we didn't explore this direction because the convergence of scene representation networks with large size images remained an actively studied problem at the time of our work. Coming back to the pipeline, although we have a pre-generated mesh file of a known shape, its coordinates are not registered to the correct space yet. We registered mesh using differentiable rendering. After that, we project mesh onto each HDR texture using the camera matrices obtained previously to finally generate the UV maps for each view. To perform the registration, we apply a differentiable renderer named SoftRes. It can rasterize a grayscale silhouette image of the mesh given a camera matrix. We extract the ground truth silhouette from each input texture and optimize a spatial transformation of the mesh to minimize the difference between the rasterized silhouette and the ground truth. With the LumiGraph reconstructed, we're ready to move on to the rendering stage. Before rendering, we need to perform a manual focal plane calibration to make the virtual scene geometrically aligned with the real scene. Since different observers tend to have different IPDs or place their eyes at different locations, this calibration has to be performed per observer. During the calibration, the observer moves the virtual dots shown on each focal plane to their corresponding locations on the physical calibration grid. The calibration will generate a rendering matrix for each focal plane to relate the world coordinates of the 3D scene to the screen space of our display. Here, as you can see, after the calibration, the virtual dot is well aligned with the physical one. This way we can correctly render the LumiGraph to be aligned with the observer's view. Here, we show some results and evaluation of our work. The first figure shows a photograph of a virtual object on top of the real one. The accurate spatial alignment of the real and virtual objects demonstrate a perceptual match in geometry. Comparing them side by side shows a close perceptual match in appearance as well. We can also vary the depth of the virtual object while the camera is always focusing at the near focal plane. As you can see, the virtual object gets blurry when it's outside the camera focus. But we have a limitation that if the camera focus is set to be in between the two focal planes, the virtual object won't be as sharp as the real one, since both focal planes are defocused. Now, imagine there is a black box inside which there is either a real object or a virtual object rendered by a 3D display. If a naive observer cannot tell which one is real, we can say that the display has passed a visual Turing test. A visual Turing test is a common notion in computer graphics to evaluate realism. But there is one slight issue of this version of the visual Turing test. What does real mean? Realism is a subjective interpretation and relies on the prior knowledge of our daily experience. To avoid such subjective interpretations, we propose a variation of the visual Turing test, where instead of showing two stimuli and asking which one is real, we show three stimuli composed of either one real plus two virtual objects, or two real plus one virtual object, and we ask which one of them is different. We tested 4 conditions in our experiment. We rendered virtual object either on the near plane or both planes. This is to test whether defocus blur or inaccurate accommodation is more critical in affecting realism. Rendering on both planes will result in both planes defocused, while accommodating in between, but rendering on near plane only will lead to inaccurate accommodation. We also include 2 control conditions with slightly reduced contrast. This is to ensure that our experiment is feasible and the participants can perform the task correctly. The results show that reduced contrast made it easier for participants to detect the difference, as expected. In the best scenario, an average observer performs the task with a detection probability of only 0.44. Note that this probability has been corrected to compensate for random guess. Only a 0 probability indicates a complete perceptual equivalence between real and virtual objects. Meanwhile, rendering on near plane gives a better result than multifocal rendering, showing that at least for this experiment, defocus blur plays a more important role than accommodation. But we cannot generalize too much with this finding, since we've only performed one experiment, and here the real object is quite close to our near plane. Finally, I want to emphasize that although we didn't achieve a complete perceptual equivalence, our version of the visual Turing test is a much more challenging task than comparing 2 stimuli. Differences in certain insignificant aspects, do not necessarily degrade the quality of realism for the stimulus viewed in isolation. All participants reported that if they had not been asked to look for differences from a physical stimulus, they would have deemed the virtual stimuli to be real. For the future work of this project, we plan to test more robust scene representations for arbitrary geometry and topology. We also plan to integrate our rendering with eye tracking to avoid manual calibration for each observer and explore the possibility to show parallax as well. We plan to test the optimal depth resolution of a multifocal display based on the evaluation of perceptual realism. Additionally, we plan to experiment with more advanced multifocal decomposition algorithms to compensate for the previously mentioned incorrect defocus blur in multifocal rendering. Finally, we plan to explore a 3D quality metric for the evaluation of 3D displays in terms of perceptual realism. Please visit our project page for more details. Thank you for attending the presentation. I hope you enjoyed it.